Okay. Can you see my my slides?
No, I think you are not sharing it.
Yet. Here we go.
No, Baman, yes, we also cannot see them.
Yes, now we can see.
And now we can see.
Yeah.
Okay. Any idea if I can make this full screen? What is the shortcut in Mac to make this full screen? I can't remember. Instead of seeing this like that. If you have any idea, let me know how I can make this full screen. Is it? No, it is not that. No, okay. Well, in this this forecasting book club session, I'm going to present chapter 5 of the FPP3 book. So this is the third version of the book by Heinemann and Antonopoulos. So this chapter actually is dedicated to what they call a forecaster's toolbox. So why they call it like this? Because all the principles and all the R functions they discuss in this chapter, you can apply them to any forecasting method or model you're using later. We discuss actually, first of all, just briefly go through a tidy forecasting workflow, because we can do forecasting in many different ways, but here their focus is on tidy forecasting. Again, this is aligned with, you know, tidyverse or tidy data analysis in general. And following that, so there are a couple of steps we need to go through here, and following that we look at some simple forecasting methods, and then we show how we can specify a method, and then how we can train a method or model on some data set using R. Of course, here we talk about the Fable package. And after that, we talk about fitted values, residuals, and we talk about residual diagnostics. And basically here we just say whether the model we're using for this particular time series could use the systematic patterns available in the data or not. So the idea of residual diagnostic is not to select the best method, but instead just see whether the method uses the available information or not. Following that, we discussed briefly about, in addition to point forecast, we discussed about distributional forecasts and prediction intervals and how we can get them in R. And then we can discuss about transformations, how we can forecast with, if we need a transformation, how we can do it in R. Then there is a section dedicated to forecasting with decomposition. So again, here we discuss how we can decompose and use that decomposition to produce the forecast. And then the most important part of this for me is actually 7 and 8, where we discuss how we can choose the most accurate forecast from a list of forecasting models. Now let's look at the tidy forecasting workflow. So in forecasting process, to, you know, in a typical forecasting process to generate the forecast, we have to go through this step. We have to prepare the data for forecasting. We have to create a sort of graphs to understand our data, and then we need to specify a model. And then following that, we need to train the model on some data. And then finally, we calculate the accuracy of the model using some metrics. And then we produce the forecast with the data set we have for the future. So if you're familiar with tidyverse, this is actually a sort of thing we have in tidyverse as well. So what we have to tidy our data. So the data set we're working with must be in a tidy format. And then we may need also to here to prepare the data. So what we mean by preparing data is we have to check for duplications. If there is any missing value, we have to deal with that, maybe because not all forecasting models can deal with missing values. If there is any outlier, so we have to figure it out and then see how we can do it with that. And then finally, you know, make the data in a format that is suitable for forecasting. So in this particular case, we are interested in a data data structure that is testable, and we have discussed this before. So to do forecasting with this book, with using Fable package, we need a an object that has a testable structure. And then we explained in the previous chapters how to create a testable. So after preparing the data for forecasting, of course, we can visualize this. We have introduced some functions in chapter 2, but you could also use all the functions in ggplot in tidyverse to create any graphs. And then now, in this chapter, we actually explain how to specify models, how to train or estimate the parameters, how to evaluate the forecast accuracy, and how to generate the forecast. So, well, this is just an example from this variable, from this data set, global economy. Again, if you haven't attended the previous sessions or you didn't read the book, so you need to install FPP3 package to be able to, access all the data sets we have here. So here we look at this data set that contains GDP of many countries. So here we filter the country to just look at the Sweden, and we use autoplot to create the time plot of this of GDP for Sweden. Again, this is just a simple time plot, but we discuss about seasonal plots, sub-series plot, and autocorrelation plot, and you can look at them to better understand the data here as well. So now, so what I was trying to do here, we have actually done these two things previously. We discuss in detail how to prepare data for forecasting, and then we look at the visualization as well. So that's why we skip these two steps, and then we go to the step where we need to know how we specify a model in Fable. So if you have used a formula-based functions before, this is exactly the same here. So to specify a model in Fable, you have to use a formula. And then this formula has, let's say, two sides. In the left-hand side, we have the response variable, and this is the variable we want to forecast. And then you have this tilde, and then in right-hand side, you have some terms. Here we call them specific functions. So depending on which forecasting model we use, we may have different terms or specific functions. So this is how we specify a model, so using a formula. So now, when it comes to forecasting model, there is a function dedicated to each forecasting model we cover in this book. And all models we use here, they are in capital letters. So this is, for example, time series linear model for regression, for time series regression. So if you do this using Fable, this is the function you have to use. And then after, inside the parenthesis, you have to provide the formula. So what happens if you ignore the formula, like ignore the tilde and the specific function? So this will be considered as an automatic method. So you have to go and look at the function and see by default which arguments actually you have if you ignore this part. So that's how we specify a model in Fable here. But after specifying a model, we have to train it into some data sets. So how we do it using a model function. Okay, so here we specify it, and this is the name we give it to actually this model, right? This is your choice. You can write whatever you want here. So after specifying a model, we train it using model function. We train it on this data set. And inside this data set, we have many time series. We have 263 time series. Again, this is because this data set is a testable format. And then one of the advantages of testable was, we can have many time series at the same time. And when we apply one forecasting model, it would be applied to all time series we have. So this is my time series. I use a pipe operator, and then I fit a model, which model, this model, and then this is the name I give to this model. So if I run this line and I assign it to this new object and I observe this object, this is what I see here. And we call this a model table or a Mabel. So what we see inside the Mabel is, so each row is one time series. And of course, each column here is one model, because here I applied only one model, so I see one column. But if I had more models, then I could see more columns here dedicated to each forecasting model. If I have only one time series, then I will see only one row here. So what is inside this? This is the fitted model. Later we will learn, if you're interested, you can go and look at inside this, to see the parameters, the estimated parameters, the information criteria, the standard deviations of errors, etc. So there are many things inside this. You can extract them and observe them. So far we just learned how to specify a model and how to train it on some data using functions in Fable. So following that, we have to actually produce the forecast. And how we do it, we pass the label, the previous one we had here, to the function called forecast. And then what we put inside this is the forecast horizon. So the forecast horizon is each equal, and then here you can put different things. You can put a number, or you can put just a natural language, as we see here, 3 years. So this is the equivalent of, let's say, 36 months, if my time series is monthly. Or at some point, actually you have to, instead of providing an edge, you may pass some data set to the forecast function. And this is the case where you use additional information. Instead of just a pure time series, you have exogenous variables. And in that case, you need to pass a data set to forecast. So you'll see later when we talk about regression in the chapter. So now if I run this line of code, this is the outcome of this. This is the output. So what is the output? Again, is a forecast table, and we call it Fable. And then here, what we have in the Fable, again, I have one row for each time series. So now what we see, in addition to the variable I had in my initial data, this is what this is my key, basically, in Tissable, which includes many different countries. I have a new name called .model. And again, if I have multiple models, then I will see them here. This is my index. Again, if you remember, in Tissable, we have key and we have index. The index is a temporal part of my data. And then after this, I have, again, I think this is, I think, the previous version, but they have updated this. So you might see slightly different things if you run it in Fable. So here, I see basically a distribution, and I see one number. Okay, what is this number? Is a point forecast, and this is basically the forecast distribution. And this is one advantage of using Fable, because you can get easily the probabilistic forecast or forecast distribution for any time series and at any particular period. Okay, so what is important to remember here, in Fable, we have a column called .model, and then we have both point forecast and the prediction intervals. And the distribution. And from the distribution, we can extract anything we want. We can have mean or average, we can have median, we can have prediction intervals, we can have any quantile we want to get from the prediction interval. So this is the whole property, and we can extract whatever we want from this. And then when I apply the forecasting model, then I can go and visualize it as well. Okay, so again, this is just a simple visualization of my forecast. So far we have learned how to specify a forecasting model, how to train it on data, and then how pass it to a forecast function to generate the forecast. So there are two important things to remember. One is label, which includes our trained data and models, and one is Fable that includes the forecast. So in the Fable, we need to remember we have the point forecast and we have the distribution of the forecast as well. So now we haven't really discussed any forecasting models so far. So now let's introduce some simple forecasting models and see how we can apply what we have learned so far. But what is important to remember, this is going to be the same for any forecasting model we will cover later. This is why we call it toolbox, because we can just simply repeat these steps for any forecasting model. Well, this is, there are a couple of examples in the book in terms of what is the most appropriate forecasting model to use for this time series. Of course, this is a quarterly time series from Australian beer production. So you may see there is a sort of seasonality. We don't see really any trend. So you may guess which sort of model might be appropriate for this. Again, here, we see, okay, of course, there is obvious trend. There might be seasonalities, but it's difficult really to pick from just this graph. You may need to look at something else. So obviously you need a model that takes into account the trend for this. Here, I don't think that there is any sort of seasonality in the data, but we may see, you know, the trend, but to change the structure a few times. So here we have it like this, and then it's increasing, and then it's reducing, and you have a like huge reduction here. Again, maybe, I don't know, because this is a stock market, I would say a simple method like naive should be used. So the idea here is just to present some simple models and see how we can apply them in Fable. So the first model is just a total average. So basically here, it doesn't matter where you are in your history. So you just take the average of all the observations, and this becomes your forecast for the future. So the forecast for the future, as you see, is the constant. So while I'm here, I take a simple average old observation and use it to forecast for the future. So what we see here is YT. So YT is the observation at period T. And whenever in this book we see Y hat T, that hat is for the estimation. So here it means I want to forecast for T plus H. So for period T plus 1, T plus 2, T plus 3, etc. up to T plus H. So H is steps ahead. And there is a condition here, conditioning on I have the data from the first period to period T, right? So this is how we read this. And this for simple average is simply equal to all observations, the summation of all observation divided by total. The second simple method we use here is naive. So the forecast in naive method is equal to the last observed value. So if I want to forecast for the future, I look at the last observation and I just keep this for the future. So if I forecast for each step ahead in the future, the forecast would be again the same. Another simple approach similar to naive is seasonal naive. But here, instead of looking at the last observation, I look at the last season. And what is the season here? Again, it depends on the granularity of your data. For example, if it's quarterly, then to forecast, let's say, the Q1 of 2020, I look at the observations and the Q1 of 2019. And finally, we have another method called drift. It is similar to naive because it takes the last observation, but it adds a decreasing or increasing trend to that last observation. So it takes into account the changes from the previous to the last observation. So you may realize actually we have the functions for this 4 different methods. So this is mean is a function we use for total average. Naive is the function we use for simple naive. Seasonal naive or S naive is the model, is the function we use for seasonal naive. As you can see here, so this has a specific function called the lag. So again, it depends on which type of time series you're looking at, but if you have a time series with multiple seasonality, then you may need to provide this lag to say, for example, in daily cases, are you looking at the last week or you're looking at the last year? So depending on that, you may specify this. And if you don't do it, I think it will automatically, it will take the last week as a lag. And then for drift, we use the function RW, and then here we need this specific function called drift to say, well, this is actually the drift method. Well, yeah, this is the graph. It is, as I said, you know, it takes the last observation in, it takes also the first and the last observation, and then takes based on this equation, right? H divided by t minus 1. Okay, so these are very simple models or methods, but you might be surprised at some, depending on circumstances, they could be very powerful as well. And then in general, in forecasting, at least we use this simple method as benchmark. So whenever you want to develop a forecasting model, you have to at least compare it with one of these simple approaches and see how good is your your proposed model comparing to a very simple model like seasonal naive or naive. Or seasonal naive, of course, you use it in a case when there is a strong seasonality in the data. So if there is no strong seasonality in the data, you may actually use naive. But just you need to keep this in mind as well. So now how we specify models and how we train it, it is exactly like the example I show you. So here, again, we use a data set for Australian production. And if you observe this data set in R, you will see that it contains many different production like beer, like bricks. So here it is just a simple filter to say, I don't want to have any NA or missing value in brick. And then, so you can just consider this as my, my data, right? And then I model it. I want to train models on this data. Which models? Here I have seasonal naive. And then here, this is my response variable, the variable I want to forecast. So this is the name I give to it. So seasonal underscore naive. And then this is my first model. And you observe here, when I want to include more model, I just put a comma after each model and I just include more lines here. So, and this is, the second one is naive, the third one is drift, and then finally I have me, right? So if I run this chunk of code, and then if I observe my Mabel, this is what we have here. And as you can observe, I have only one time series, then I have only one row, right? And as I mentioned, now I have in my Mabel, I have different columns for different forecasting models. So what is really important to remind here is, again, because everything in Fable is like a table. So if you are familiar with data frame or table, and if you know how to work with them using tidyverse, then you know actually how to deal with this table, how to extract information, how to select things, how to filter things, how to create new variables using mutate, etc. So this is really powerful because I can do forecasting, but still I can do it in a tidy way, and I can use all the capabilities of tidyverse packages. So now we specify 4 simple methods. We train them, and then here I simply I pass my fit or my Mabel. I pass it to my forecast function, and I can generate the forecast for 5 years. And then this is, again, what I mentioned. So I have that model. So there is a list of models here. Again, this is my index. This is the point forecast, and I have prediction intervals. And I have a distribution. I don't know what I keep saying prediction intervals. So this is the distribution. And then as you can see, it's actually a normal distribution. So in Fable, we mainly generate the normal distribution. But if you believe for any reason the normal distribution is not appropriate, so there are other ways to generate forecast distribution using simulation or using bootstrapping. And I will show you in the book. It is not in the slides. So here I generate the forecast, and then I take the forecast or the Fable, and I can create a visualization with that. So here what you realize is I pass the whole data set to autoplot. So I pass the Fable, but then inside autoplot I put the data set, I passed it to my model here, right? And you can actually try it without this, and you will see what happens. If you do this, you see only the forecast. But because I want to see the actual data as well, so I put the actual data here, And I put the level equal to null because I don't want to see the prediction intervals here. I just want to see the point forecast. And then here you can see how different models are forecasting the future for this particular time series. Well, this is the whole example for another data, this for Facebook closing stock price. And actually, if you go to the book, you have it for Google, right? Well, it is the same data set that contains the closing stock price for many companies. So here, the example is for Facebook. But if you go to the book, not sure if you can see it. Can you see the website?
Yes, we can see.
Yeah, so here you have exactly the same, I mean, not exactly the same, but a similar example, but this time it's for Google. So I thought maybe it's a good idea to keep both because you see how it works for both. So let me go back to my slides. Yeah, so what happens here, again, I have a data set. And then inside this data set, I have a couple of different variables, and I want to group by symbol. And again, the symbol here is corresponding to different companies. Here I create a new variable called trading day, and the trading day is simply actually looking at the raw number of my my initial data set, and then I put it in a new name. And then here, because this is initially a testable, but because after grouping and creating this new variable, I want to update my testable. So if you want to update the testable, because here if you look at it, your index is different, but here I want to update my testable. So this is the function I use, and then I put my index equal to trading days. The trading day underscore day, this is just the variable I have created. And then this regular equal to true is by default actually is equal to true. It means I have equally spaced periods. So if you have unequally spaced periods in your data set and you want to create a testable, again, I think I gave an example, you have to put regular equal to false. For example, if you work with hospital data set, and then in hospitals you have arrival time. And arrival times are not equally spaced because you may have a patient that arrives now, another one arrives 2 minutes later, another one arrives 5 minutes later. So they're not equally spaced. If that's the case, you put regular equal to false. But again, this is something you have to go and read in chapter dedicated to testable in I think chapter 2. Okay, so again, so after this, well, we have ungroup. As a good practice, whenever you group based on a variable, it's good to do ungroup. Again, this is something related to metadata. It creates a new data structure if you don't ungroup it, and then maybe later it creates some issues. So as a good practice, it's good whenever you group by, you ungroup after that. And then here I filter the symbol. I want just to look at Facebook data, and I assign it to a new object. And then now it's easy, you know how to do it. I pass that object to model, and then I specify here 3 different models, and I forecast for 42 days. And then I can also go and visualize it. And this is basically the outcome of this code. So this is for Facebook. If you go to the book, you can do it for Google as well. Well, if you want, you can work on this, but we skip this one. So now, so you learned how to specify, how to train a model, and how to forecast, and how to visualize the forecast. Now let's look at the concept of residuals and the residual diagnostic. So to understand the residual diagnostic, I mean residuals and residual diagnostic following that, we need to first understand the fitted values. So what we mean by fitted value, now basically fitted values are just the forecast of one step ahead. So if you consider, you know, the time series you have, in each period, you can forecast for next period, given that you have all the information up to, you know, the current period you are in. So you can, you know, imagine this process from your first observation and continue from the first observation up to last observation. So in each period, we generate the forecast for next period. right? And this will give you, for each actual value you have in your data, it gives you one estimated value, right? And we call this a fitted value. So there is a difference that we'll say in terms of terminology between residual and error. Some people may refer to them both as error, but here we distinguish residuals from the error. So I'll discuss about the error later. When we refer to error, we mean actually more the difference between actual and the forecast in test sets. But here residuals, I'm looking at this fitted values, which are one step ahead forecast. So what is the residual in forecasting? The difference between observed value and the fitted value, right? I don't know if I can go to the book to see whether, yeah, let me see if there is anything here. And of course, I will show you some stuff later. I was just wondering if, yeah, I don't have that line. I wanted to see if there is any line like fitted and actuals they can show you. Doesn't matter. Okay, so now we understand what is the fitted value and we understand what is the residual. So we can actually talk about some assumptions that we need to verify, and that's what we call the residual diagnostic. If you have a forecasting model, and this forecasting model is capable of taking into account all the systematic patterns in your data, then what is left over must be completely random, right? And so that's why the concept of residuals, because residual is the difference between the actual and fitted. It means whatever is inside, I don't know, this object of residual, so this must be something random. So there are a couple of assumptions we have to verify to check whether these residuals, they look random or not. And one of them is the autocorrelation. So if you look at the time series of residuals for any forecasting model, they should be uncorrelated. And then again, maybe how to do it. You can look at the ACF, autocorrelation function, and then all the autocorrelation legs for residuals should lie between the interval or the blue lines, if you remember ACF. So that's the first condition or the first assumption. The second assumption is the residuals must have a mean equal to 0. I mean, at least theoretically equal to 0. And then if they're not, then forecasts are unbiased. So these are two important assumptions related to point forecast. There are two more assumptions related to more prediction interval and distributions. And one of them is the residuals must have a constant variance and they should be normally distributed. And again, this is for the condition where we assume a normal distribution, but if you believe this is not the case, then this is not probably important. So these are four important assumptions to consider when it comes to evaluate the residuals. One important thing to keep in mind here is we are not looking at residuals to select the best model. We're just looking at the residual to understand whether the forecasting model we are using is capturing all the systematic pattern in the data or not. And this is completely different from what we do later, where we evaluate the accuracy of the model and we select the best model based on the forecast accuracy in the test set. I think this is important to remember. So now we do, again, we use an example of the Facebook, but again, in the book, I think this is based on Google. So this is the time series of what we have seen previously. And I can apply a naive method because this is a stock market, stock price, then it is likely that naive is doing a good job, but let's see. So basically here I took, my data, which is this one here, which is this time series, and I pass it to model and then a naive, and then what I want to forecast, because inside this you may have a couple of variables, I want to forecast close, the closing stock price, right? So this is what we did, I mean, maybe you notice here, I didn't put any name for it, right? I didn't put any name, and as you can see here, it takes this as a name. But if I had, let's say, my naive equal, then here you see my naive as a name, but because I didn't provide it, you know, you see automatically it generates this as a name, okay? So now the important thing here is to extract fitted values and residuals, you have to use a new function here called augment. So you can pass the Mabel or the fitted values or the fitted models onto this function, and this function, it gives us actually more information. So in addition to the other variables I have in my data, like symbol.model, and then the trading day, and this is the variable, again, the actuals I have here, it gives me the fitted and the residuals as well, right? So normally, if you calculate the difference between the actuals and the fitted values, they should give you the residuals. Okay, so I think and this is just a new function to extract this, and this is something maybe you need to note. And while you see it here, it is very close. We cannot really observe it, but we fitted the data and then we plot them. So here we have the actuals and here we have the fitted values, right? But because they're very close, we can't see them. So the difference between these two lines, the green and the red one, actually gives us the residuals. But if you look at the part of the data, not everything, if here I filter to just look at part of my data, and now I can actually see it. And there is a lag actually, of course, between these two because the fitted values are based on naive. So the difference between these two lines will give me the residual, and this is actually the residuals. Well, in many parts, actually, they look like random, well, except probably here. I think there is a jump there that the naive model is not capable of doing it, I mean, understanding it. So that's why we see this jump in the residual. So it is actually left over. And probably that's just the only thing, but the rest, it looks like a random time series. If you look at the histogram of residuals to see whether it is like a normal distribution, well, of course, you know, you have a long tails here, so there are a couple of things here that actually makes it not like a normal distribution. And then if you look at the ACF, you see for the majority of legs, you know, they are inside this blue lines. And so in terms of the point forecast, I think it is fine because majority of them are inside the blue line. There is just this one and here a little bit this one, but they're very close, so that could be just something random. So yeah, so in terms of residual diagnostic, what you need to do is you need to look at the augment, and this augment, it gives us everything we need in terms of the actual data, the fitted value, and the residuals, and we can check them to see whether they look like random, whether there is any pattern in them. Of course, we are interested in a residual that doesn't have any pattern. And then finally, we need also to check the distribution, whether they look like random or not, and whether the variance is constant or not. For example, from here, you see that, well, I think the variance is more or less the same, except again, this one thing here. So for the ACF residuals, we assume that the residuals are white noise, and that's what I mentioned. They're uncorrelated, they have zero mean and constant variance. And then if they are not, it means there is information left in the residuals that should be used in computing forecast. And probably this is the most important thing in residual diagnostic. Again, I repeat, you're not here to select the best method. You're just here to observe whether the model you're using can capture the interesting or genuine information in the time series or not. And if it's not, it means, well, we should probably use a method that can do it. Yeah, so I think, yeah, so, you know, instead of using these diagrams, we can actually do a statistical test. And the statistical test can tell us whether the residuals we're looking at are random or they're not. So there are two tests here we're looking at. So there is portmanteau and Young-Bucks test. So the function we use here is features. So again, we extract the residuals using this, and then we can test them using this function features. And I want to test residuals, and I want to go for the Young-Bucks. And then this degree of freedom is actually related to number of parameters. If you're using this test for raw data, then you have to put degree of freedom equal to 0. And if you use it for a model without parameters, like naive, then you put it equal to 0 as well. So if this p-value is higher than 0.05, it means actually your data looks like white noise. And then this is the case for our data. Well, you can use this function, gg_ts residuals, with your Mabel. So you pass the Mabel to this function, and you can get these three graphs together. So a scatter plot or for the residuals, an ACF, and the normal distribution. So you can look at them all together here. Okay, I will skip this. I think I have a lot to cover. Let's see how much of this I can do. So following this, now we look at actually the forecast distribution and prediction intervals, because so far what we look at in terms of generating the forecast, I said, well, in the fable we have the point forecast, and then we have another column for the distributions, right? So you remember when we discuss about y hat t plus h, when we actually show this in the forecasting model, this is actually usually referring to the mean of a conditional distribution, where we have yt plus h conditioning on having all the previous observation. And for many forecasting models we have in Fable, so we can get normal distribution for the forecast. And then, as I said, this distribution can describe the probability of observing any future value. So you get actually a distribution that has all the properties of the forecast you want. So assuming our residuals are normal and uncorrelated, then we have the standard deviation equal to sigma hat here. So we can generate for this simple models we have here, we can calculate mathematically the forecast distribution using normal distribution for these four methods. And this is the equation. But when, for the other models, it becomes complicated to calculate the distribution of the forecast over each period ahead. When it comes to prediction intervals, so the prediction intervals gives a range. So in the distribution, we had all the possible values, right? We consider the forecast variable as a random variable, and then we can get all possible values of that. But in the prediction intervals, we can actually give the region, like a lower bound and upper bound. And then we have an interval, and this interval is corresponding to a probability. And then we say with this probability, we think the forecast will lie between the lower bound and upper bound. And again, this is the coefficient that corresponds to the probability we are looking at. Again, there is a table in the book that gives you this coefficient for each probability you're looking at. So to get the prediction intervals, we have the point forecast, and then we add and deduct that coefficient that corresponds to the confidence interval or prediction interval we want times the estimation over the h steps ahead. Now, how we extract these prediction intervals is actually using a function called hilo. So here I have my fable, and then I pass it to a function called hilo, And then inside Hilo, I can get any prediction interval. 95%, 90%, 99%, any interval you want. So what is important to remember here, why we talk about distribution and prediction intervals, because if you just focus on the point forecast, then there is no uncertainty with the point forecast. So basically the point forecast somehow ignored the uncertainty. And if you want to report the uncertainty around the forecast, so it is important to also consider both prediction intervals and probabilistic forecast. So in terms of how we do it in R, I think we don't need to be worried about how this is calculated, because we automatically, I mean, for all the forecasting functions we use, we automatically get a probability distribution, and then we can extract any interval we want to have there. So there are, I mean, many things we can discuss about prediction intervals or probabilistic forecasts. They are actually in the book, in the version 3 of the book, they touch upon some important points in terms of, for example, prediction intervals, how narrow or how wide should be, in terms of, you know, if you increase the forecast horizon, by increasing the forecast horizon, most of the forecasting model prediction interval would be widened as well. I think there are a couple of important things in the book you need probably to consider there as well. And so following that, we need to look at the forecasting with transformation, and this is pretty easy. Again, depending on the situation, at some point you may need to use a transformation, you need to transform the response variable to produce the forecast. So it is extremely easy to do it with Fable. You just need to put that transformation before your response variable. So instead of using turnover here, I use lag turnover, okay? And by doing this, I'm actually doing a logarithmic transformation on my response variable. And you know, the rest is the same, so I don't change anything. So now, again, I just, you know, as I did previously, the only thing, I add a log here before the response variable, and I pass my Mabel to the forecast, and I get a Fable here. And as usual, I get the point forecast and prediction intervals. Again, if you go to the book, so in the book, they explain different things in terms of when you apply the transformation. Normally, you don't get the median. You don't get the mean of the forecast distribution. Instead, you get a median. But then, you know, in the Fable, they did this automatic, so you don't again need to be worried about this. So this is actually what I'm talking about. If you apply a transformation, instead of, you know, getting a point forecast as mean, this is what we expect from a point forecast. We know it as a mean of our distribution, but you get a median. But this is automatically considered in the Fable. So whenever I use a transformation, I get actually the median, the mean, sorry. But if you want to get a median, that is possible as well. So I think this is the argument you need to use. So inside the forecast function, if you want to, you know, to get the median, so put the bias underscore adjust equal to false. If you use of course, a transformation, right? So if you don't use it, automatically this is equal to true, and then you will get the mean automatically. So whenever you do a transformation, if you care about both mean and median, so maybe you can just put this equal to false as well to get the median from that as well. But if not, if you're just interested in the point forecast in terms of the expected average or mean, so this will be automatically, you know, transformed back to the median using Fable. So in terms of the transformation, so one important thing to remember is you just put the function related to the transformation you want just before the response variable, right? And then again, you need to maybe keep this in mind as a second option, as an argument. If you want to have the median as well, just put it equal to false. We can also use decomposition to do forecasting. I think we presented the decomposition chapter previously, so you might be familiar with the decomposition. So again, this is the data set related to United States employment, and we look at just a part of that because here we filter our index. And this is the data in the testable format we have for this. So when it comes to forecasting with decomposition, because we can decompose the original time series to trend, seasonality, and reminder. So basically what happens is we apply a forecasting model to a seasonally adjusted data, and then we apply another forecasting model to just the seasonal data. And we finally combine these two things together to get the final forecast, right? So if I want to apply the decomposition, and then here, again, there are different ways to decompose. Here it is based on STL decomposition. So I can apply this STL decomposition to the variable of employed in this data set. And then I can actually check the components. So this is a new function again. We will talk about this in regression, ARIMA, and exponential smoothing more. And using this component, you can actually extract the different components of an object. So here in this case is STL. So we can have the actual, and then a separate column for trend, for seasonality, and then for the reminder. So basically here, what we did is we just did a decomposition. And here, as you can see, I can apply a method like naive to seasonal adjusted data from decomposition, and I can forecast based on this, and I can plot it as well. So this is one way to do it, but you don't need to be worried too much about doing it manually, because we have a function in R that actually does it for us. So the function is decomposition underscore model. So you have to pass the STL to this decomposition underscore model. And then here you just need to provide which function you're using for forecasting seasonal adjusted data. Automatically, this decomposition underscore model is using seasonal naive to forecast the seasonal part, but you need to provide what is the function you're using to forecast the seasonal adjusted data, right? So again, if you're interested in using forecasting with decomposition, this is what you need to do, right? So you have your data, you pass it to the model, and then the only thing we have, which is different from the previous one, instead of the just having the model, we need to use another function inside this, which is decomposition underscore model. And then the first argument of this decomposition underscore model is actually the decomposition. But again, I have explained this in the decomposition chapter. You need maybe to go and have a look if you want to know how we decompose. The second argument is the function we need to forecast the seasonal adjusted. And then when we pass it to the forecast, it actually put these things together and then gives us, the forecast, the distribution, the point forecast, and if you want, you can extract any prediction interval from that as well. Okay, so finally, I think this is probably the most important part when it comes to a toolbox, because so here we covered how we specify a model, how we train a model, and then we realized that, okay, from forecasting part, we can get a point forecast, we can get a prediction intervals, and we can get the whole distribution as well. And then we can actually do it if you want with the transformation, or if you want, we can decompose and then forecast. Now, how we know if a forecasting model is accurate? Because this is the way, we can select the best model and use it in the future. When it comes to evaluating the accuracy of the model, imagine you have been given a time series, right? So you have a time series. What you have to do with this time series is, first of all, you have to train your model with this time series, But at the same time, you have to use the same time series to evaluate the accuracy of your forecasting model, right? So one option that comes to our mind probably would be, yeah, let's use all the data and fit a model to this data and then evaluate the accuracy based on this. But this is not a good idea. Again, I think we discussed this previously, but there is a concept of overfitting, right? So you may get a best fit on your data, and this is possible. We always can get a perfect fit on our data. But the perfect fit doesn't necessarily give us a good forecast, right? And this is an important concept to remember. So there are two things that we have to avoid when it comes to forecasting. One is overfitting, and the second one is failing to capture systematic pattern in the data. Because in the data, we have systematic patterns and we have random variations or noise. Of course, we can't do anything with noise. We are just interested in genuine or systematic pattern in the data. So a good forecasting model should capture that systematic pattern and then, project it into the future without overfitting, right? So how then, if we cannot just use the whole data to fit and to evaluate, so what we need to do, well, we need actually to separate or leave out a part of our data, and then we assume or we pretend we don't have this data. This is our new data. So we apply the forecasting model to the rest of data, and we test it, based on this new data that we call it test data or out of sample data in some textbooks. So this is again fundamental. When it comes to forecast evaluation, we have to evaluate the accuracy of the forecast on a new data and not the data we have used to train our models. Okay, so if I forecast for my test data, then at the end, again, I have now actual values and I have the forecast I generated. So I can calculate the error. This is what we call the forecast error. And that's what I said, I distinguish an error from a residual. Residual is for fitting. Error, I use this term when I calculate the difference between actual and forecast in the test set. So I can calculate the error. So error for each period, t plus h. H again is 1, 2, 3 up to what we want, which is the horizon. So the difference between the actual and the estimation of the forecast, right? So if you remember when you talk about residuals, I mentioned we have the fitted values because the residual is equal to actual minus fitted value. And fitted values are one step ahead forecast. But here, when you talk about the forecast error, actually we talk about multiple step ahead forecast as well. And the error we calculate from this are now true forecast errors. And if later on I judge how accurate is the forecasting model based on this, well, I'm pretty confident because I have tested it in a new data set that has not been used for the training purposes. Well, I can, apply a forecasting model using this four forecasting models to this data, and I can plot them. Well, you see that they're quite different. Seasonal naive, somehow follows them, but again, I'm not sure if it's the most accurate one. And then I will never, visually evaluate the accuracy of a model because it's not a good idea just to do it visually based on one sample. Okay, so now we talk about the error, but the errors are for each period. What if I want just to have one single number and then evaluate how good is the model based on that number? So that's where we talk about accuracy measures. So basically, accuracy measures are the functions that help us somehow to summarize the errors across different periods. And we have many different accuracy measures, so many different ways to summarize the errors. So here we have a mean absolute error. So we calculate the error for each period, and then we calculate the absolute value of the error, and then at the end we take the mean. We can have mean squared error. Again, we take the error for each period, calculate the square, and then we calculate the the mean or the average of it, well, we can have root mean square error, where we can actually take the square root of what we calculate here. In mean absolute percentage error, so we calculate the error and then the absolute value of error, and we divide it by the absolute value of the corresponding actual observation. And then we calculate the mean of it, and then we multiply it by 100 afterwards. So there are many, as I said, many different accuracy measures. So you need to go and find out which one is more appropriate for your forecasting exercise. What is important to remember, there are some accuracy measures, we call them scale dependent accuracy measures, but we have some accuracy measures that are scale independent. So if you are working with many time series, and then those time series, they have different scales, then maybe you need to be careful, because you need to use a scale independent accuracy measure that allows you to compare the accuracy across different scales as well. Again, each of these accuracy measures, they have their advantages and disadvantages. There are a couple of good papers. Again, if you're interested, let me know. I can send you that discuss, this various accuracy measures. Well, there is another accuracy measure called mean absolute scaled error. The problem with this, the first one, mean absolute percentage error, is scale independent. But the problem with this one is, if you have 0 values in your time series, then this cannot be calculated, because it's division by 0. Division by 0, and we can't do this. Then some authors, they propose alternatives, and one of the alternatives to deal with this is mean absolute scale error. And then here we have again the error, the absolute of errors. This time we divide this by Q, and then what is the Q? Basically, the Q is a naive forecast on our training data set. So again, as you can see, this is just the difference between the current observation and the previous observation, and then we calculate the summation of this, and we divide by the total number of observations. Well, there are 2 versions of this. One is for non-seasonal, and one is for seasonal. But this will be automatically calculated in R as well. Okay, so, well, this is an example of now how we calculate the forecast accuracy. Because remember, this is what we have done. You know how to do it now. We have a data, then we pass the data to the model, and then we specify the models inside this. And then if you run it, we train these models in our data. And then here we know how to calculate the forecast. Well, it doesn't have it in, or it has it, sorry. Yeah, so, and then following that, how we calculate the forecast accuracy. If you just pass the fitting value or the Mabel, if you only pass the Mabel to accuracy function, it gives you, some accuracy measures for the training data. Well, this is not really interesting for us, because we want to have something for the test data. So to calculate the accuracy for the test data, you have to pass the fable and then the original data you have that includes both training and test. And if you pass this to accuracy function, now you can actually get the accuracy measures for all the methods, right? And then which one do you choose? Well, we choose a method that gives us the lowest error, which actually here corresponds to lowest accuracy measure. So the one that has the lowest, the smallest value, I think it's, it is seasonal naive here. So seasonal naive is the best method based on what we have done here. But is it all? Well, not really, because this is not the most robust way to do it. So why? Because if I evaluate my accuracy only based on one sample, I'm not very confident, because my forecasting model has been only tested on one situation or one single sample, right? If I want to be more confident, I have to design an experiment that allows me to evaluate the accuracy of my forecasting in many different samples or many different situations. And that's the concept of time series cross-validation. So in time series cross-validation, we start by dividing our data in two parts, test and training. But this time, the size of my test is quite high. In general, as a rule of thumb, I put 70% of my data in train and 30% of my data in test. And then what I do is, then I start by my initial training data and I forecast for what I want. And then I include one more observation from what I forecasted, and I forecast for next period. And I continue doing this, right? And this is for one step ahead. If I have multiple steps ahead, I will do the same. Well, I think I have something maybe in a blog post. I don't know if it makes sense just to quickly show you this. And then I think I have to maybe stop here. Yeah, I don't know if you can see this, but this is basically what I mean. Can you see this page?
Yes, we can.
Yes.
So basically, this is my entire history, and this is my future, right? So basically, what I did in this case is I said, well, I can start by actually last observation, and I leave out the number of observations equal to my forecast horizon. And the purpose of actually doing this is just, at the end, I want to visualize my forecast on this 4 periods because my H is equal to 4 here as an example. So if you want, you can ignore this. But as a practice, I always do it if I have enough data. And then what I do with the rest is I create an initial training. I fit a forecasting model to initial training, and I forecast for the horizon I want. Next, I include one more observation in my training, and I forecast for the forecast horizon I have. Next step, I include one more observation in my training, and I forecast for the forecast horizon. And I keep doing this up to a period where I have only the number of observations left is equal to my forecast horizon. And I cannot continue after this. And then now we call this an ID. So actually I create different time series, different samples, different situation, whatever you want to call this. And then now I test the capability or the accuracy of my forecasting model in these different situations. And then that's the purpose of time series cross-validation. So there are different ways to do it. Normally I use this function called slide_testable. Let me see if we have anything here. There is an animation, but that's not really helpful. Yeah, so this is the function I use to create time series cross-validation. So this is my data. And then I pass it to stretch testable. So there are two important arguments here. This .init is the number of observation I put in my initial time series. And this is actually corresponding to what I show you here. It's corresponding to this yellow part, the initial time series. And what is the second one? The second one is that step. And this is corresponding to how many observations I include in my initial time series every time. If I include one by one and I increase the size of this initial time series one by one, I put it equal to 1. If it's, let's say, more, I put it more, right? And if I just run this, and then here, of course, I'll just ignore this, but if I run this, what I get now, actually I get a new testable that has a new name called .id. And this .id is corresponding to different time series I show you there. And then now I can actually pass this different time series to my model. And again, this is exactly what we have done previously. So we can put this in the model function using any model I want. And now what happens is this model will be applied to every ID or every time series. And that's why we see now I have many rows And each row is corresponding again to one time series, and in our case is one ID. And then I pass, now this time I pass this to the forecast, and I forecast for one step ahead in this case, but you can do it for any. So what is important to remember, you know, the way we specify a model or the way we forecast doesn't change at all. The only thing that is different now is we have to pass our data to a stretch underscore testable function to create different IDs or different time series, and then we continue, training our model or passing it to the forecast as we did previously. And then now we can judge based on actually the cross-validation. We shouldn't judge based on the training. We always judge based on the cross-validation. And then whatever this cross-validation tells us, then that is actually the best method that I can use for the future. So there are a couple of important things that they are not here, but they are in the book. So when it comes to evaluating, so in the book, there is a new section called 5.9, and I think this is important to go through as well. So, you know, what we covered so far in the slides, we were looking at how to evaluate the accuracy of the point forecast using root mean square error, using mean absolute error, and other criteria. But here in this section, it covers actually how to evaluate the accuracy of your prediction intervals and your forecast distributions. And then here there are three different measures. So one of them is the quantile score or percentile. So again, here it calculates a percentile for each period. So depending on, you know, whether that percentile is below or above the actual value, it gives it a score. And at the end, you can get a total score for each quantile you're interested in. And you can also do the same now with the prediction intervals with Winkler score. So again, Winkler score can be calculated for any prediction interval level you want. So here, Winkler score covers two things. One of them is the width of the interval, how wide or narrow it is. And then the second part is the penalty. So depending on whether the actual observation is below the lower bound or above the upper bound, it gives a penalty to that as well. Again, we are interested, of course, in a score that is lower. And then finally, there is also a probabilistic score called continuous ranked probability score. And you can also use this to calculate how accurate are different forecast probability distribution for each method. So again, have a look at this. If you have any question related to this probabilistic accuracy measure or prediction interval measures, please let us know. But they are, Shishwan is here as well. He's familiar with this sort of thing, so he can help with that as well. But I'm happy to, you know, to answer any question related to this. I think this part is very important. So if you haven't read it yet, maybe it's worth to go through this. So I think it is time. I think I have a meeting in 10 minutes. So I will stop recording.